Okay, good morning or good day to everyone. How are you this morning? My name is Pauli Jokinen. I'm a meteorologist here at FMI. I work at the climate service, so I'm basically the link between the researchers and the general public and media and different companies. So I do lots of this exchange between experts and just a regular layman. So what I'm going to talk to you about for the next half an hour is how to combine data. What's the good things about combining data? So I will use some reanalysis data, some in-situ observations, and impact data. And basically I'm going to show you a storm case study from last year, and just to give you some sort of an example of how to do this in reality. So let's get to it. My motivation is basically started last year. We had several strong storms in November and December last year that caused quite a bit of damage. We had, I guess, several 100,000 people were left without power, as Petteri Talas talked about this morning. And we got a lot of questions about where the storm was the strongest, where the strongest winds were, what was the area that had the biggest impacts, and etc. So media is interested about this. They want to know right away, which areas were the worst hit. Also, insurance companies need that information because they start to get claims about, we had a tree fell over our car, so is the insurance company going to pay for that or not? There was one guy from a forest center in Finland who needed some sort of information about the areas that they should look at, if they want to hire a plane to fly over the areas and do some sort of inventory about the storm damage. So a lot of people want that sort of information about where the strongest winds were and where the biggest impact was. And they want it right away, of course. They can't wait for a week or a month. So what we had ready was just this kind of a map showing the highest wind gusts for one particular day. This sort of map over here, which is basically just for our meteorologists. And you can't really get a good sense just looking at it quickly of just to get an overall view of where and how strong the storm was. So I wanted to do something to combine different data sets so that we can get a quick overall view just looking at one map. And the question is, can we do that, and how is it doable? So that's my motivation. Again, as has been mentioned already this morning, is that one data set doesn't necessarily give you the whole truth. You might have a reanalysis data. It has its good sides and it has its bad sides. Actual observations, they give you some information, but they are not necessarily the truth. So if you use many different data sets, then you can do the analysis yourself and just think about, okay, this is good for this data set is good for this particular view, but the others might be better. So it's a good idea to combine data sets. So what I did, I combined the data sets, and then you can quickly kind of compare gridded reanalysis data and in situ observations. I will show that in a minute. And this way you can maybe pick out the unrealistic or suspect in situ observations by comparing it to the reanalysis data, or you can do vice versa. You can see how much the reanalysis kind of smooths out the extremes. So you can get those sorts of information right away. And additionally, I included some information about the impact. So you could basically pick out the wind gust speeds at those locations where some damage occurred, and then you can see what is the threshold when damage starts to occur. So let's get to it. When I was planning on how to do this, I was going to do it with graphs, which is a good tool for visualizing gridded data sets. But usually, programs that are already made, they can do some things, but they might have limitations if you want to do all sorts of things at the same time. So what I did was I decided to program everything myself with Python. I know it sounds daunting, but it's something that I wanted to do for a long time. I'm not an expert programmer, and that's why I wanted to try if I could do that. And Python is a quite easy to learn language. It's easy to use. It's quite commonly used already in the scientific community. So it's a good thing it's a good programming language if you want to do both programming and visualize the data that you have. Because there are packages already available that you can very quickly plot everything on a map. So I want to show the strengths of using the Python language as well. Now the data sets that I used was the ERA-Interim reanalysis, gusts. Those are post-processed parametricized gusts from the reanalysis. Additionally, I used the FMI's maximum gust observations. And lastly, we have this data set that we get, which is basically emergency call data. So when the storm comes to Finland, some trees fall over, people call to the emergency number saying, okay, our roof tiles are being blown off, or if there's a tree gonna land on top of my car, they can make that call, and we get that sort of information to FMI right away, so that we can get information about where the strongest impacts were. So I'm going to combine all of those three data sets. Now, I won't go through the Python script because I only have 30 minutes. It's not that long, but it would just take too much time to go through it. But here's basically the structure that I did. First, we extract the gust data from the grid file of the reanalysis file, and then we calculate from all of those time steps. We calculate the maximum gusts for the storm period. And then finally, we plot that data on a map as a shaded background. So that's part one, just using the reanalysis. Second part is I import the data file that contains the impact data, so all the calls made to the emergency services. I convert the coordinates so that we can plot them. And then because we have, I guess we had like several thousand calls during the storm, you can't really tell easily where the most impacted areas were. So I decided to smoothen the data by basically doing this, it's called a kernel density estimate. So basically just plot the densities on a map, because it's easier to then really quickly see what areas were the most impacted. And then I plot those contours on a map as well. And for later use, I also picked out the ERA maximum gusts from those locations where damage occurred. I'll talk about that just in a second. And the third step is just import the gust observations from our database and plot those observations as circles on the map with the same color scheme as used in the reanalysis. And as I said, I picked out the maximum gust from the reanalysis for those locations where damage occurred. Then we can plot that on a histogram to see what the thresholds are when damage starts to occur. But this is all theoretical. Let's have a look at what it actually means. So you can run the script by just this command and giving it an argument called ERA, so that it plots, it extracts the gust data, calculates the maximum values, and then plots it on the map. So this is basically for the storm period, the maximum gust from the reanalysis data set. So this is already quite good because you can see that, okay, the strongest gusts were coming from Norway and Sweden, and then the mostly affected areas were according to the reanalysis here in central Finland. But basically, this already gives you some good idea of what the wind gusts were and what the areas were affected. But of course we want more, so that's part one. Part two is getting the impact data. So you get something like this. Here, individual, the small dots are the calls made to the emergency services. So as you can see, you get the general idea where the calls were made, but again, I wanted to simplify it even more, and so I did this density contours on the map as well, which are these lines over here. So you can see that the most affected areas, damage-wise, were from this from the coastline over here in western Finland and all the way to southeastern Finland. So this is the area that we're talking about. Now you can probably see that there are these clusters here and there. So for example, here's a cluster, over here is a cluster, These are, of course, areas where you have the bigger cities where people live. So that's something you have to keep in mind, that if you want to do more statistical or more scientific work, you have to take into account the population density as well, so that you can basically normalize these values, so that you don't just look at areas where people live. For example, if the same kind of storm affected northern Finland, where the population density is a lot less, you wouldn't get this sort of a map over there. So that's something to keep in mind as well. So that is the density information about the emergency calls that we make. So then the last bit with the separate files, this is our observation network and the maximum gusts that were reported for the storm period, again plotted on a map. Now, of course, you can, you know that most of the strongest wind gusts were measured over sea areas or along the coastline. You can see that they are brighter red or orange, and also these circles are bigger. But if you want to get a good idea about inland stations, you can't really tell easily from this figure what the most affected areas inland were. Again, because it's in situ observations. For example, if you look at this area over here, you have a station over here that reported 18 meters per second wind gusts, and right next to it you had 29 meters per second. So actually this station is right in the middle of a larger lake, so that's why it's a lot more. But you have these issues with the in situ data that you would have to take care of. And if you just needed to say what the strongest or the most impacted area was from this figure, you can't really easily pinpoint the path of the storm. But again, you get the magnitude of the storm by looking at the strongest measured wind gusts. So those are the three components. They are individual, but can we combine all of that? Yes, we can. This is just one example how you can do that. So you have the shaded background here is the reanalysis wind gusts. Again, showing this area over here with the stronger wind gusts, so basically over 22 meters per second, according to the reanalysis, with some higher values along the coastline. Then you have the impact data on top of this. So I didn't plot the individual dots here because it would make them bigger, more cluttered, and I just wanted to smoothen it out with these contour lines. So you can again see that it kind of matches with the reanalysis data fairly well. Now, of course, it doesn't mean that where you have the strongest wind gusts that you're going to have the most damage, because here in the north, if you have strong soil or ground frost that anchors the trees to the ground, you might have strong wind gusts, but there won't be that much damage because the trees don't fall over that easily. So they don't always go, in the same areas, but nevertheless, you can see that from this kind of a map as well. And so additionally, you have the circles depicting the maximum wind gusts from our database as well. So all of the three things are now plotted on the same map. If you want to, you could give this out to media, to insurance companies, you could give this to people who need the information quickly, just to get an overall sense of how strong the storm was, which areas were the most impacted, and etc. So that's what I wanted to do, and maybe refine this tool a little bit and use it in the future as well for our climate service side. So again, this is just one case study. It's one example, but it's sort of like a climate service. It's not climate change service as it is, but you could expand this quite easily to cover that as well. But I mentioned that I also did a histogram. So this is just one example of how you can use the same framework and go much further. So what I did was, again, if I go backwards, for each of these locations, for each of these dots, I picked out the maximum gusts from the reanalysis gridded data set. And then I plotted that on a histogram. And what you get is something like, just go through these, is this. So here on the x-axis, you have the reanalysis maximum wind gusts in meters per second that we use here in Finland. And here you have, it's sort of like a normalized probability for this particular case, but you could just plot the number of cases as well. So what you can see from this is that in this particular case, the damage started to occur when wind gusts were about 19 to 20 meters per second, which is a good amount of information if you want to, for example, use this for forecasting studies, but also it gives you some sort of idea for climatologists as well. So you could do the same thing, for example, for summer months and winter months and see how much that varies if you use more data sets, more data, not just this one case, but just take more storms and more data, then you could get much more information about when do you actually start to get damage from wind gusts. And basically, if you do the same thing for southern Finland and northern Finland, see how much that differs, you could do all sorts of this data. But here you can see that there's this big drop when you go to wind gusts over 23 meters per second, and that is just because, if you have a look at this, there aren't that many areas inland where you have gusts over 23 meters per second. So the area is so small that you don't get those values. But if you again had more storms and a larger time frame, I would imagine that this would be more like a I don't know, normal distribution kind of a curve in this histogram. So that's what I wanted to show you, and again some notes about this. As I mentioned, the impact data, if you have access to that, I encourage you to get that sort of information if you're interested in this, or maybe just, you know, it's something that we've had for some years now. We don't have a long data set of impact data, but I would guess about, I don't know, 3 to 5 years or so. But as we get more and more, then you can do more studies, and again, take into account the population density. But one problem with this is that people want these sort of maps right away, basically the next day that the storm went through. And the issue with this is that the ERA-Interim reanalysis, you know, it takes time to make that, so it's available maybe 2 to 3 months afterwards, so we can't use that reanalysis data. Ideally, if we had, I don't know if I can, you know, if somebody can get the message out, it would be ideal to maybe have some sort of a first guess reanalysis, maybe just a few days afterwards, that we could use in these kinds of examples. Or if you don't have any possibility to get that in, then you can search for other reanalysis or analysis tools like LAPS or some other mesoscale analysis tools for data. You could alternatively use model forecasts as well for the background shaded map, and do a quick forecast validation as well if you wanted. So, actually I'm a bit ahead of time, but that's no problem. Basically what I want to show you was what you can do with Python, first of all. It's a really easy to learn language. If I can understand it and learn it, then everybody else can, because I'm not an expert in programming by any means. So I encourage you to have a look at it. It's really good, and there are many ready-made packages so that you can plot these sort of things easily on a map and do all sorts of statistical analysis as well. Now, I did a script that has all this that I did. Everything is commented. So if you want to use that as a basis, you can. You can just pick out pieces of the code for your studies of what you want to do, but you have to modify for your cases. So this is only for this particular case and for this Finnish area. So if you want to work with it, you have to do some modifications to the script. Now, I mentioned some things about the benefits of combining data. Again, one data set doesn't give you the whole truth. If you combine different data sets, then you can see the benefits and the weaknesses of them and do the analysis yourself quite easily. And as I said, reanalysis is just one aspect in this particular case. So again, you can get the idea of what the benefits are of combining data. So some suggestions that you might do in the future is, for example, again, take a longer time series and compare the in-situ observations to the reanalysis. You can do that very easily with Python. Just maybe calculate the maximum wind gusts from your observations, the maximum wind gusts from the reanalysis, and see how much they differ from each other, for example, get some sort of bias estimates, for example. Now the gusts is one of the hardest variables in my opinion. So you can do the same thing with temperature, precipitation. So this is not about gusts at all, but I work with wind a lot, so I wanted to use that as an example. So some other suggestions is that you could, again, if you have some sort of a bad weather station, or that you know that underestimates wind gusts, for example, it's covered by large buildings or a lot of forest, you could very easily just get an estimate of how much it is underestimated by, assuming that the reanalysis is the truth. So that's just one example. There are many things that you could do. And again, you could do the damage histograms with different parameters. For example, something that I might do is have a look at snowfall and what are the thresholds when we start to get car crashes, for example, in the main Helsinki area or up north. Everything like this is very easy to do by this script and modifying it just a little bit. So, as I said, I only have 30 minutes, so I didn't want to go through the script, but the data and the instructions, this presentation, everything is on these computers. So if you want to have a look at it today or tomorrow, you can and see how it works. It's basically just run the script command and give it an argument, which is explained in the instructions file. So if you want to have a go at it, you have to go to the terminal with these computers, and it's in the data folder. And I guess it's combined CORECLIMAX folder as well. So if you want to have a look at it, I can help you with that. And from this link, you can download all the data, the script, instructions, everything. If you want to have a look at it at home as well, so if you don't have time today or tomorrow, it's no problem. You can try it yourself. And if you find bugs on the code, please let me know. There are probably bugs in there, but I'm still a novice with this sort of thing, so please let me know as well. So that's all from me. If you have any questions now, please ask, or if you have any questions later on, I'll be here today and tomorrow, so I can help you with this. So thank you very much. Any questions, or should we go to? Yes.
Could you have done this? You mentioned forecast data, so can you elaborate a bit more on this? Wouldn't it have been better, maybe? Don't they have higher resolution and they would be, as you said, faster available? So why not do it with forecasted data in the first place?
Yeah, that's something that I thought about doing. You could, again, those are the same type of files. They're usually grid files or NetCDF, so you can implement that easily. The thing is that, again, it's forecast data, so we've seen cases where even the forecast from maybe 12 hours before the storm is, I don't know, flawed. I don't want to use that word necessarily, but you can do that. I mean, it will probably work and give you some sort of a basis as well. It might not be the same that you would get from a reanalysis, but again, as you said, it has a better resolution. You will get more of the finer detail as well with the current model. So that's what I'm planning to do next, and just to see how much that would alter basically the map. So for example, here you have, actually I forgot to say, this is from labs data. So it's basically we do an hourly analysis based on our observations. So here is I guess the resolution is 3 kilometers, so you get the idea of how much finer detail you get. The problem with this is that it's not balanced yet, so you see these bullseyes that are basically just coming from the observations, so that's the problem with this sort of data set. But again, forecast data would work quite well as well, so that's something I'm going to do next. Was there, yeah?
Yeah, this was a very good presentation and technical capabilities. And but I was thinking about if you do this for the weather component, that's a technical problem. You combine different data sets and then to get some estimate on the best estimate on the prepared conditions. But if you combine these with impacts, such as the phone call, emergency phone calls, those are basically the aggregate from all different sectors. And what does the number of phone calls represent actually? If you do this damage histograms based on the wind thresholds, how is the emergency phone calls in some like other time days? because this is a specific day with a specific weather event. So what do those actually represent, the emergency call?
Yeah, the emergency calls, we get sort of like a filter to data, so we don't get all the emergency calls. If someone has a heart attack, we don't get that information or anything like that. So we just get the information that is when the call is made, the person receiving the call makes a small, fills a form indicating that this is related to kind of like prevention of more damage usually. So the data that I used here is filtered already so that it's mainly related to, in here in Finland, about either roof tiles or something blowing that then the fire department needs to go and fix, or there's a tree falling over. So this particular data is again works fairly well with storms, but again we have more data coming now that is related to car crashes, for example. And of course, if you have a look at there are where is it? There's a dot over here, for example. This might just be a bogus call that is not related to this case. So there are probably a lot of individual cases here that are not related to the storm, but because of basically the number of observations, we can assume that most of them are related to the storm because they are already quite filtered that we get. So, but it's dependent on the day of the week and a lot of different things of how many calls we get, and again the location where the storm affects. As I said, if you go up north, we might not get any calls because usually you don't get much damage over there. Did that answer your question?
Yeah, and in addition, I see this very valuable if you combine this with different impacts in different sectors, and you are able to define the threshold as well.
Yeah, this is something that is quite new. So again, we've had this only for a few years, but as we get more experience with this and we get more, we can filter the data more, then it's more useful in the future as well. Yes?
I think the sort of Python scripting you're doing is what I would call some of these very important tools that actually contribute to the capacity of the whole community, especially when you're willing to share them, and that saves other people reinventing the wheel. I guess I've got a mixture of questions. The first one is to the whole audience. Like, if we just have a show of hands, how many people actually use Python scripting?
Very good.
And how many don't? Yeah, that's even more surprising, I think, because it really is very powerful.
Yeah.
But then related to that is what would encourage more people to use it is if they feel they can get hold of these tools, and it's the sort of thing that's very common for other bits of computing. If you want an algorithm to sort some data or something, you can go onto some sort of search engine and sort of just ask the question. You'll find lots of people have posted different ways of doing it. What's your feeling for the sort of meteorological or climate service type scripts? Are there people out there who are posting their things on the web to make it easy for other people to get hold of and adapt, and encouraging that whole philosophy that whenever you write something, you put it out there and let other people improve it, and then you benefit from their improvements?
Yeah, there's again, as I said, just in the last few years, the amount of people using Python in the scientific community has really gone up a lot, and also in the atmospheric sciences as well. I got a lot of problems with this, but all the problems were solved. I went to Google, did some sort of search, and there are lots of people asking questions, again the same things that I had, and they have really good answers as well. So all the information that if you get stuck, you usually find on the internet. If you don't, just put your questions online, and I'm sure that there are people who are ready to answer those as well. So that's one of the huge benefits nowadays with the internet, and so that you don't need to ask someone in your department or who knows something about this. Just go online and you usually get the answers, and there are already made programs for statistical work and that you need also in the atmospheric sciences, and I expect that there will be a lot more scripts in the next few years that people then can just use and modify for their own needs. So that's why I wanted to learn Python as well. So that it's a language of the future, I guess. Yes?
Thanks for your excellent start with the training course. I like the example very much. A question related to what you said at the beginning is you said that this is a climate service. Okay, you also mentioned, okay, this is different than climate change service. Okay, can you please reflect on that? If this should be tied to the climate change services, what features do we need more than this?
Yeah. Again, this was basically more a basic climate service that we do every day. You know, if you have a storm, then afterwards the storm comes to our group from the forecasting office. You know, we deal with the storm afterwards. So this is something that is just a case study, and it's more related to climate service. But if you want to expand this to climate change service, again, the same tools apply. If you want to do more of a time series type of stuff, or have more data and have a look at trends, and as I said, you can download packages for the Python interface that really quickly you can do linear statistical stuff to the data. So again, the basic tools that you have here, opening the grid files of the reanalysis, all these different steps you can then use if you want to do climate change service as well. So I used just this easy to understandable example here, but again, you can modify this very easily if you want to do more of a climate change studies or service as well. Yes, do we have time? Yeah.
Very quick comment in the sense of, because I think there is really a need for this exactly for climate kind of applications. When you look at storms and emergency things like afterwards, but Finland is one country in having this 112 number data set being freely open and classified quite well, which helps to use it. But in the world, this many times happens for social media, let's say messages, so Twitter analysis or something like that. Haiti, for example, as an example. There's a lot of the kind of applications who try to help just by the messages. But I think this is exactly where some of the kind of high analysis would be good to combine those old data sets in a way from them to see how can we better analyze what went wrong and good also with climate information or the weather incident or something like that. So in essence, it's not necessarily many times climate change towards forward, but I think a lot of the things are to understand, especially storms and impact. So that's what hurts us. It has to be better found in the past, to be kind of like also seen in the sense of reanalysis is very comparable to climate prediction models. It's better comparable, not very good. It's better comparable to that than to use just observation levels. From there, I think when we have from the past statistically analyzed well things, we should then be able to sometimes say in the future in climate change that, okay, this type of like damages or incidents we have in there, so have a better grip on it. And that's why I think we definitely need these kind of ulterior data sets and how to use and visualize them compared with reanalysis.
Yeah.